Thank you, Natalia. I'd like to welcome you all to the first workshop of our conference. As Natalia said, it is the workshop on new marine IMTA cultivation opportunities, so integrated multi-trophic aquaculture opportunities, and we will be discussing both our open water and our land-based systems. So first of all, I'll just show you the... So here's our program for the next couple of hours. So I'll just show you, as I am now, the workshop format, and then we will move on and we'll have presentations on our land-based systems. So first we will hear from Luis from the Brazilian system. Then I will have a video from our... Oh, thank you. I will have a video from our colleagues in South Africa who unfortunately couldn't be with us for this workshop. Then we will move on to the open systems, and again our colleagues from the Scottish Marine Science Association couldn't be with us, so we'll have another video then, and then I will present to you the Irish IMTA Lab. Then our colleague Thomas from Argentina will present the prospective IMTA Lab. So we have 5 IMTA Labs in the ASTRAL project. 4 of them are currently functioning. They're producing species, and the 5th is a prospective lab in Argentina. So without further ado, I will kick off and I will pass you over to Luis to give his presentation on our Brazilian IMTA. But I suppose just a quick refresh for those of you who may not be fully familiar with integrated multi-trophic aquaculture. You can see here it is a system whereby we grow multiple species in one environment, and this allows for organic and inorganic waste produced by one of the species to serve as nutritional inputs to the other species. So the waste is used as nutritional inputs, and this eliminates waste and creates a circular system. So with that, I'll hand you over to Luis to talk us through the system that he has here in Ferg, which is a biofloc system. So I'll give you over to Luis.
Okay, thank you for the invitation. I will talk about our production system at Ferg in Rio Grande do Sul. We start to work with IMTA system to solve problems with our production. So probably you have the same idea. This is like the pointer is. We have problems with total suspended solids and nutrients in our system with bioflocs. So we have the biofloc, the density of biofloc increase during the shrimp production process. So we need to solve or remove this excess of biofloc, and normally we use mechanical systems. So why not use other kind of animals to remove this excess? It's the same process to nitrate and phosphate. So if you have the same perception that me, where we have this simple puzzle, you are partially wrong. This is not work easy. The solution is not easy. Doesn't matter if you work with open or land-based systems. Look like the same thing. If you look the target to know different species, production cycle, structure, oceanography, or water quality conditions, basically is the same, but it's more related to different puzzles with a lot of pieces that we have to work together to know how is the best configuration to the system work well. So we need much more information than we imagined at first. So in our case, we performed different things, different experiments to, at the end of this presentation, I will show you, this is the best configuration, is that. To know this, we need a lot of information, and we performed a lot of experiments. Basically, our systems is, we have our main species is the shrimp, Lithopenes vanamae. Then we move the water, we pump the water from the other tanks with fish. In this case, we start with oysters and fish in the same tank, but now we know it's impossible to work together in the same tank. Then, by gravity, the water with biofloc come to seaweed tanks, and then flow to, by gravity, again to the shrimp tanks. So we have the recirculation system all the time, 24 hours, 7 days a week. And we stimulate the biofloc production by organic fertilization. So we we introduce sugar in the system. Then the bacteria would use this carbon and the nitrogen, especially ammonia and nitrite, from the excretion of the organisms in the system. So increase the biofloc, the water quality is good, we can reuse this water all the time. And the most important thing, the biofloc is a good source for food for the animals, especially Lithopenes vanamae, and in this case is tilapia too. Well, I put the wrong presentation, no problem. I would like to show the water with biofloc. This is a dirty water. This is a brown water. So if you look the water, you will see, oh, God, you're crazy. So the idea is to put our organisms together in the same system and take advantage from this organism. So we perform different experiments to know how many shrimps we can introduce, because it's very important to determine the relation between the shrimp biomass, fish biomass, algae or seaweeds, halophytes, oysters. It's important to know the relation between one and other species. And of course, everyone here look for more productivity system. So we start to work with 250 shrimp per square meter. This is equivalent to 25 tons per hectare cycle. This is a lot of shrimp. And now we work with 45 to 47 tons per hectare cycle. So to find this productivity, we work a lot, we perform different experiments. With oysters, it's the same. We work with different species of mollusks. We try to work with Cassostrea gigas, the Pacific oysters, but didn't work because the temperature is higher, especially to produce shrimp and tilapia. So the Pacific oysters don't like this. So we change the species, start to work with local species, Cassostrea gazar. This is a local species that support high temperature and the variation of the salinity in the system. When I talk to you about the tilapia in the system, we work with reduced salinity in the system. We work with 20 parts of salinity. And the Pacific, the oysters, it's basically is the limit to work with Casustrea gigas. So Gazar, no, it's not a problem. So we start our studies with Gazar. For example, when we start to work with tilapia, we decide to work with 30, 35 fish per cubic meter. But at first we imagine if we increase the density, increase the consumption of bioflux, so it will be better. But no, this is not correct. We have to work with 30, no more than 20, 35 fish per cubic meter, because tilapia help to produce more bioflux in the system if we work, for example, 100 or 200 fish per cubic meter. So and it's possible to produce tilapia a lot of in these densities, but our goal is maintain the water quality. So it's more important for us in our IMTA system work with reduced densities of tilapia. 35 or 30 tilapias per cubic meter is a lot of tilapia. So, but it's better to work with these densities to keep the system work in good conditions. Okay. We know now, if we work with these densities, it's possible to control or to maintain the total solids concentration. When I talk about total solid concentration or suspended solid, I'm talking about bioflux. This is a live organism, a live microorganism in the system. Okay. So with these densities, it's possible to keep some level of the bioflux in the system working for us. Respected to seaweed, we try to introduce different species in the system. Our best species that consume nutrients was uva flexuosa. I don't remember the species. This is uva flexuosa. This is a filamentous algae. So the consumption of nutrients is very, very nice. But the problem is the algae move to the other tanks. And sometimes enter in the pump, in the submersible pump, and the system didn't work. So we change. Now we know it's much better work with uva fasciata or uva lactuca than other, because the leaf, if I can name this leaf, is large. Then we don't have problems to move the algae to another tank. So this is the game. We need to find different species. Related to the bioflux, bioflux reduce a lot of the light in the system. So now we know that it's important to keep the algae close to the surface, because it's obvious, but now I know. We have more light on the surface. And if the algae is 40 centimeters from the top, the performance is not so good, or it's not good. So we have to move the algae close to the surface, 10 centimeters, to obtain the best result, to obtain the best performance of algae. So reduce the nitrogen in the system, and especially phosphate. Algae is very, very good consumer respected to phosphate. We try to introduce 1 gram, 2 grams, 3 grams per 1,000 liters, and the best configuration or the best biomass is 1 gram per thousand per liter. We perform a lot of experiments to know this now. In respect to halophytes, it's another important plant that we can introduce in the system to help us to absorb nutrient, especially nitrate, but the halophytes like more phosphate than nitrate. So we solve the problems with phosphate with halophytes, algae, reduce 30 to 35% of nitrite in the system, but we need to find another species, another kind of plant to reduce more the nitrogen in the production system. So we had good. Now we know the positive results. It's possible to produce shrimp and tilapia. It's very, very nice, very easy to produce these animals. We have good food conversion rate. For example, compared to conventional system to shrimp production, this is 1.2, 1.3 kilos of feed to obtain 1 kilo of shrimp. This is better than traditional system. But especially for tilapia, the food conversion, traditional food conversion for tilapia is 1.6 to 1.8 kilos of feed to obtain 1 kilo of tilapia. And in our system now, the food conversion rate is 0.4. This is much better than the profit that the producer can obtain with this is much better. So this is very, very interesting result. We can improve the circularity. We can reduce or reuse the water. Now we know we reuse 95% of our water in the system. So it's very, very interesting system. We can reuse this water for 2, 3, 4, 5 cycles. So we can reuse this water for a long time. If we reduce more the nitrite concentration, we can improve more the reuse. Another point is very, very interesting is the relation with older groups of research, especially with the group that work with technology. So now it's easy to work with these groups because we know the people and they know us. And for example, now the concentration to produce Cassostraea agassar, we know is 200, no more than 250 grams or milligrams per liter. How we know this now? Because we put sensors on the oysters, and with the sensors told us when the oysters open and close the valve. If the concentration is more than 250 milligrams per liter, the oysters close, don't eat, and die. But if the concentration is around 200 or 250, the oysters open and close or eat during the life. So we know now about the consumption about the oysters because this kind of integration. So it's very, very nice when we work with different groups. It's very, very important to develop the aquaculture in general. Okay. And we had negative points. Now oysters and seaweed had problems because the temperature is one factor. High temperatures for shrimp, or good temperatures for shrimp and tilapia, 30, 31, 32 Celsius degrees, the algae don't like this temperature, and the oysters don't like too. So we need to find another form to introduce these species, maybe during older period, for example, during our winter period, where the temperature decreased to 25, 26 Celsius degrees or 24. Maybe this is the moment to introduce oysters, introduce the algae in the system. We will do this now. And we need to find other species that consume nitrogen in the system to reduce especially nitrate in the water. Some pictures from our system. This is our shrimp tank, the oysters, seaweeds, the tilapia that work with in our tanks, and the halophytes outside in the system. So really the main results, we know we now the food conversion rate. It's possible to perform 2 cycles of shrimp to obtain 1 cycle of tilapia. Some results interesting to work into. This is the weight, the growth of seaweeds. It's important where we have biofloc. If in nature of we settling the biofloc, the protein concentration content in the seaweed is higher than when we work with other kind of water. So it's possible to produce more seaweed biomass and obtain more protein inside in the algae when we work with the biofloc. Finally, if you have interest, you can see these publications related to ASTRAL project. And this is, I received the information today in the morning. This is a new one, publication that you can see this, and you will see the evolution, how work the system, and you can obtain more information about this. I show, in general, the best results. Okay. Thanks. If you have any question, please, I will be happy to answer. Yeah.
Thank you very much, Luis. We might take our questions at the end of the sessions after all our presentations on the IMTA labs. My apologies, I meant to mention at the very beginning that this session is being recorded. You'll see the cameras here, so just to let you know that. So we'll move on now. We're staying with our land-based systems, and the next one is from our colleagues in South Africa. As I mentioned earlier, unfortunately, they cannot be with us today. So we have a video to show of their system, which is a flow-through system concentrating on a commercial production of ulva and abalone, and then a pilot-scale system of urchin ulva. So I will just ask them to turn on that video for you now. Thank you.
Good afternoon. I'm John Bolton from the University of Cape Town. I'm sorry I can't be with you today, but I'm going to present on the IMTA Lab South Africa in the ASTRAL project. This is a land-based system growing abalone and urchins and using seaweeds for partial recirculation. Our IMTA Lab is mainly a link between the University of Cape Town, the Government Department of Forestry, Fisheries and the Environment, and Viking Aquaculture, with some link with LATAT with respect to microbiome studies. And the main players are Brett Macy from DFFE, our postdoc Marissa Brinkole, and we have recently lost Dr. Mark Cyrus, unfortunately. Although he's still part of the project, he's now in Australia taking up a lectureship in aquaculture at James Cook University in Queensland. The cultivation initially in IMTA South Africa is based on a fully commercial system growing the abalone, the local abalone, Haliotis midday on the left, with integrated systems with Ulva lacinulata, the green seaweed ulva. This is really an abalone cultivation, and the ulva is added for various reasons, for various functions, which I'll explain. We're adding sea urchins to our systems, linking a new species, Trypneusis gratilla, a warm water urchin, also with ulva, and also adding a local urchin, a local temperate urchin, Parachinus, to abalone aquaculture for a very specific purpose, which I'll explain. So the South African IMTA Lab, most of the work happens at the Buffalojacht abalone farm, fully commercial abalone farm run by Viking Aquaculture. And also we do experimental work at the Department of Forestry, Fisheries and the Environment Experimental Marine Research Aquarium in Sea Point in Cape Town. Buffalojacht abalone farm is about 200 kilometers east of Cape Town. As mentioned, it's a land-based pump ashore system integrating the aquaculture of abalone with ulva. And the effluent from, if you look at the bottom right, all the small tanks are abalone, and the effluent goes into the ulva paddle raceways, which removes ammonia, which enables 50% of the water to be recirculated. So the objective of IMTA Lab South Africa is to develop and validate cost-effective IMTA and land-based pump ashore systems, and mainly to take the existing abalone ulva systems and attempt to optimize them, generating critical information on biosecurity, species health, and system health, and also to develop and optimize culture technology for a new high-value species, Trypneusis gratilla, in this tunnel which we built, which you can see on the bottom right. This slide is a quick history of integrated abalone ulva aquaculture in South Africa. On the top left, Wild Coast abalone in the Eastern Cape. This initial system, growing ulva in paddle raceways for feed, was built in 2002, more than 20 years ago. So integrated abalone ulva aquaculture has more than a 20-year history in South Africa. The next step on the top right was Irvin and Johnson Cape abalone in the Western Cape. And this system was built using scientific data that suggested that the ulva could be used for bioremediation and to enable recirculation. So part of this farm in around 2006 was already grown using, built using recirculation technology using ulva. And the manager who built this system then moved to Viking Aquaculture, Nick Loebser, and has since built two farms which run completely, designed and built two farms which run completely on recirculation systems. So the bottom right one is the one we're working on, Buffalojacht abalone, but they're also building a new farm in the last few years, Diamond Coast abalone in semi-desert region of the far northern Cape of South Africa, high up the west coast. So there are now two fully commercial abalone farms running in South Africa, designed and built to run completely on with recirculated seawater, with the partial recirculation enabled by the ulva, by remediating the water. So the two main drivers for the production of ulva on abalone farms, first of all, were to produce supplementary feed. This is particularly important on the warm coast of South Africa, at Wild Coast abalone, where they have problems in warm water episodes with feeding formulated feed, and they don't otherwise have access to seaweed stocks. So that was first of all. And secondly, on other farms, to allow for recirculation of seawater. This partial recirculation at 50% water recirculation saves circa 40% of the cost of pumping, It also provides a supplementary feed which saves something like 20% of the cost of feed. It also increases the water temperature in this region, resulting in improved abalone growth. And it gives the possibility, as I'll mention shortly, to protect over short periods against harmful algal bloom events. So currently, South African abalone farms produce a little over 2,000 tons of ova per year. And a main thing holding back other farms from growing ova in this way is biosecurity concerns. The idea of moving ova and water, overgrowing an effluent in the water, bioremediated back into the abalone, causes biosecurity concerns and the fear of abalone disease. The original recirculated IMTA farm no longer recirculates, but still grows ova for feed. And a new farm, which was meant to be working with an integrated system growing ova and abalone effluent, now grows ova separate in fertilized seawater, both of these for so-called biosecurity reasons. But as we've seen, two new farms built since 2014 both grow ova and abalone effluent water and use it to bioremediate the water for recirculation. So it's a mixed story. So the challenges facing IMTA development in South Africa are, first of all, biosecurity. Is there a risk associated with recirculating water and feeding effluent grown ova back to the abalone, as mentioned? But also, are the physical and chemical parameters of the IMTA system optimal for the health and growth of the cultivated species? So we're working on this. Also to do with the environment, there is an increased frequency of harmful algal bloom events. There was a very bad one in some of the South African abalone industry in January 2017. So this is something we need to think about. And also a big problem is lack of diversification. The South African abalone represents a large proportion of the value of the South African marine aquaculture industry. So it's focused on very few high-value species, and can we introduce new species into these IMTA systems? So we're carrying out considerable studies on the microbiome of these partially recirculated systems, bacteria, fungi, oomycetes, and viruses. And what we found so far is that the ova appears to have a modulating effect on the microbiome in these IMTA systems and can reduce the abundance of potential opportunistic pathogens. There's a lower bacterial diversity observed in the gut of abalone which are fed IMTA-grown ova, suggesting that ova plays an antimicrobial role in the gut. And also, together with other benefits observed from abalone-fed ova, things like improved consumption, abalone growth, and immunity, ova appears to be a clear benefit in these integrated systems from a microbiome point of view. As is the main thrust with the ASTRAL project, we're determining how closely these systems may approach zero waste while maintaining the optimal health of the animals and the system and economic sustainability. So we're doing a lot of studies on the physical, chemical, and nutrient profiles in the systems at the commercial 50% partial recirculation rate, but also turning the system up to 75% for periods and even up to 100% for short periods. The 75% recirculation, we've shown that this can work for extended periods. We've had systems at Bafokeng running at 75% recirculation for a month, and with very little difference from the 50% recirculation on these parameters above. The idea of 100% recirculation is, if there's a harmful algal bloom, can you use the ova recirculation, the bioremediation capabilities, to close off the system for a few days while there's a harmful algal bloom? And we've shown that this is possible for 3 days. This has been done twice now on the system. Obviously, we don't want to overdo it with a very valuable crop of commercial abalone in the system, but it's certainly possible for 3 days, and in drastic situations, it may be possible for a little longer. So this has potential for some mitigation against harmful algal blooms which non-integrated systems would not have. As mentioned, we're also developing culture technology for a potential new high-value species, the warm water sea urchin, Trypneustes gratilla, and also attempting to integrate it with ulva. We've built the first pilot commercial ulva IMTA system at Bofuyas. This was initially stocked with about 1,000 urchins, and we've been studying system functionality and commercial grow-out technology. There is a hatchery in the bottom right here at Bofuyas now, producing abalone urchin spat, and we also have an experimental hatchery in Sea Point at the DFFE aquarium. We've conducted a number of experiments optimizing culture technologies such as stocking densities, feeds, basket designs, and we're just setting up at the moment a full life cycle grow-out study with to end up hopefully with approximately 15,000 urchins in this system in the top right. And finally, we're trying something else with a different local sea urchin, the temperate sea urchin Parachinus angulosus. And in nature, juvenile abalone, such as these in the farm at the bottom, live underneath, almost always underneath these urchins. And so the hypothesis is that feeding the abalone with urchin feces can result in improved growth, gut enzyme activity, and survival. And so far, we're finding that this can work. In microbiome studies, there's been a clear transfer of bacteria from urchins to juvenile abalone. This has contributed to gut health, digestive processes, and growth, has shown some pathogen reduction, e.g. in Vibrios, and the introduction of this new species could improve the health and sustainability in abalone aquaculture. And this is Marissa, who's doing a lot of this work. So this is our team, Brett, myself, Marissa, and Mark, in the urchin tent, and we'll be setting up a new big urchin experiment very shortly. The urchins are settling at the moment, and hopefully we'll have a large crop before the end of this year. So thank you very much for your interest. I've put the email addresses of myself and Brett in case you want to contact us directly, but you can also contact us through the Astral websites and various links. So thanks very much. I hope you have a wonderful conference. Thank you.
Okay, well, obviously the South African team are not here to take any questions, but if you do have any questions or queries, please let me know and I will pass them on, or you can use the contact details that are there. Also, it's worth mentioning that on our Astral YouTube channel, you can see more in-depth videos about each of the IMTA labs where each of the systems are explained, so that might be worth visiting as well. So we'll move on with our next presentation. We're swapping now from our land-based systems to our open water systems. And the first one that we're going to present to you today is the one based in Scotland. Again, unfortunately, our colleagues from Scotland are not able to make it here today. So I have another video to show you. And again, if there are any questions, please note them and we can contact the relevant people if needed. So we look at our open water system, looking at seaweed cultivation and various shellfish with our colleagues in Scotland.
And it's my job today to give you a very brief introduction to our IMTA site and discuss some of the challenges that we're trying to address within the Astral project and share a couple of examples of some trials that or some work that we're doing to address these challenges. So as by way of introduction to our IMTA site, we're a 1 hectare site. We typically do most of our trials on the 1 meter to 50 meter scale. Certainly as both industries scale, we would expect to see larger farms, but the primary purpose of this farm is to optimize the techniques needed to co-cultivate these low trophic species. And so for us, we're focusing on high value shellfish as well as seaweed aquaculture. And I should say that whilst we're working on the nursery conditions and optimization of seeding for ulva and Palmari palmata, so that's green and red species here in Scotland, Primarily, it's the kelps that we've been focusing on because these are more commercially available in terms of the technology for cultivating them. In terms of the high-value shellfish, our main focus has been on the European flat oyster. The primary driver there is that there's an established market here in Scotland, and there's also an emerging market within oyster restoration. And this is particularly attractive because rather than the 4 years it takes to get a oyster seed through to table market, typically would take about a year to get that oyster ready for the restoration market. So it's just another strategy we're exploring. We're also growing king scallops at a smaller scale, as again, there's an established market here in Scotland. So just to say something about the key challenges, we want to reduce cost associated with this aquaculture activity, and we intend to do that through improved performance. And so we're developing strategies that improve the growth performance for both the shellfish and the seaweeds by trying to optimize key events. So in this case, I'll give you an example of optimizing the timing of harvest, as well as optimizing the cultivation system, and I'll give you an example of optimization of cultivation depth. We also want to improve the cultivation system, so reduce the amount of materials needed for the cultivation process, reduce the environmental footprint of the activity, as well as improving the circularity of the cultivation materials that we're using. And this is all aiming at maximizing value through improved quality. And as part of ASTRAL, we'll be producing best practice guidelines for cultivating these species and techniques to improve crop performance. So just to talk about our IMTA approach a little bit more, and in this we're really trying to exploit practical synergies between these two sectors. Most of our oysters at the moment are grown intertidally, and in seaweed aquaculture we typically use small vessels, and the cost requirements of managing a site mean that we're looking at ways to try and reduce costs associated with that activity all the way through the process. So our IMTA approach fundamentally sits with separating the oyster or the shellfish component and the seaweed component, whilst also maintaining them within the same infrastructure to increase the efficiency of that infrastructure. And so in this picture you see an example of two catenary lines holding oyster baskets, and then seaweed lines suspended between them. And the oyster system actually provides buoyancy for the seaweed system, and by separating them, we're avoiding double handling because it takes oysters up to 4 years to reach the table market, and seaweed will be ready for harvest within 6 to 7 months. We're also trying to support year-round production, so producing multiple species within the same system, and it's our hope that as the industry scales, that we will be able to observe and support ecological synergies between having multiple trophic groups represented within that system. So to use an example here, I have some data from our native oyster cultivation, and what we've done is we've monitored the growth and the growth performance, so in this case the condition index of the oyster, through the cultivation cycle, and we've been growing these oysters now for over 2 years. But rather than just look at the IMTA system, we also compared the growth and the condition index of similarly grown oysters, but in an intertidal site. So this is at a commercial oyster farm just located adjacent to our IMTA site. And as we can see, a lot of the different factors which are driving performance are typically driven by the environment. And in this case, I'm using the example of food availability measured here as chlorophyll A. But perhaps the most interesting result from this trial was the high mortality observed within the intertidal site. And the current working hypothesis is that in an intertidal site, the extreme temperature events and also the movement of water off the shore and the stress created from increased temperature may have contributed to the higher mortality in the intertidal site. And actually, this oyster farmer is starting to move his stock into the water using the same system as we're using at the IMTA site. In terms of optimizing seaweed, we've been monitoring kelp yield, morphology and composition throughout the cultivation cycle, and also comparing this between years. And I've got some data here just to show the variability within the years. And a lot of this has been driven by differences in the environment or the cultivation cycle. And so for a farmer looking to supply a food market, they may require an earlier harvest to ensure that they have the highest quality possible and to avoid any biofouling that is typical later on in the season. But for those businesses looking to supply a biorefinery approach, so the production of energy or bioplastics, they may be able to tolerate a later harvest and therefore have a higher yield. And so it's important when selecting the harvest window to understand how the environment changes every year, and also to select the most optimum harvesting period for your particular application. And the final example is optimizing cultivation depth. And I'm not going to go into specifics because I don't have very much time, but this is based on the idea that at the moment, most seaweed farmers would select an optimum depth, which is an average optimum of the entire cultivation season. And so what we've done here is we've deployed lines at different water depths at different time points in the year to understand the effect on yield and the composition of the algae. And to share an example from this, we can see that our optimum, and we've measured this over multiple years, is 1.5 if taken as an average of the entire cultivation season. But for both Alaria esculenta and Saccharina, we can see that after deployment in October, a shallower optimum is actually achievable, and we're putting this into practice to see whether we can actually increase the yield this year just by making one depth adjustment. And hopefully, if this works, it will be a strategy that seaweed farmers can use. And lastly, an important point, to make this work applicable to different sites, we're actually measuring the amount of light energy at the different cultivation depths, because this is one of the primary drivers to optimum cultivation depth, and will make this data relevant to other sites also. So I think that's all I've got time for. I will stop there, but thank you very much for your attention, and please reach out to me if you have any specific queries about our work. But again, thank you for your attention.
Okay, so please, if you do have questions for our colleagues in the Scottish IMTA lab, please note them, and we can endeavour to make contact with Adrian and Catty in the SAMS IMTA lab laboratory. Okay, so the next system that we're going to talk about is the one that I work on myself, which is based on the west coast of Ireland. So my name is Pauline O'Donoghue, and I work with the Marine Institute. I need this now. So we are an open water system, and First of all, I'll just explain why IMTA. So as Luis explained in his opening as well, that IMTA is shown to remove material wastes from species and lower the nutrient load. It changes, it can bring about changes in consumer attitudes, and this has been seen particularly in the lower trophic species such as invertebrates and seaweeds. The IMTA concept takes production from a linear model, from the monoculture typical systems, to a more circular model which affects the whole ecosystem. It provides waste reduction, which is part of the ecosystem services that the industry can provide, and it optimises the use of valuable aquaculture space. Numerous products can be produced in one area, utilising the resource more effectively and more efficiently. So you'll see here a graphic depiction of the IMTA setup in an open water system, and this is the system that I will go into in more detail. So we are an open water marine site. It's called Lehenapool, and it's the first of its kind in Ireland. We're a licensed multi-species site. The goal of the site is to look at and investigate sustainable aquaculture practices and to test new and emerging technologies. The aim is to support the Irish and the international aquaculture sector to become more circular and sustainable, and of course while protecting the environment. So to date, the research focus in this research site has been on IMTA, and we're testing the validation of sensors, new technologies, using a multifunctional monitoring approach, and this informs then the management systems for the site. So our species and our site selection have all been subject to suitability assessments, and just bear with me while I get my notes, because I'm going to tell you about up to 10 species that we have cultivated on site, and I don't want to miss any of them, so I'll just refer to my notes. So you can see here that this site is based in an enclosed bay on the west coast of Ireland called Bertabui. It's nicely sheltered from the fetch of the Atlantic. You can see here that we have 5 fish pens, and in these pens we grow salmon. We also have a multifunctional raft which we use to carry out the husbandry on the site. And then we have modelled this whole bay to look at the nutrient flows, and we found that the nutrients that are produced by the fed species in this area flow to the south of the site, and you'll see here that this is where we have introduced our low trophic grid, and on this low trophic grid we have our seaweeds and our various mollusks and crustaceans. So the low trophic grid is a new structure. It was introduced towards the end of 2021. It is co-located with the salmon pens, and it is directly connected to the grid of the monoculture system. As I say, it's downstream of the modelled nutrient plumes, and this is to maximise the uptake of the species that are being grown in that low trophic grid. It refines and expands the capacity of the low trophic species, and it has allowed for the extension of the long lines from which we hang all our species, and this has proved to be a more adaptable system, and we can do various different avenues of research for that. It has a less visual impact, and we all know that this is very important when you're dealing with aquaculture, as the aquaculture has caused controversy in many areas in the locations where it is being carried out, and to be able to allow for a less visual impact is always a bonus. There are less moorings and less anchorage, and this has allowed a reduction in costs and reduction in physical infrastructure by approximately 50%, and again it is a better utilisation of the space. So the reason that we have developed this system is to be able to show monoculture farmers that the introduction of an IMTA approach can be more attractive and can prove to be a better use of the aquaculture production areas. So you'll see here the fed species are in the background. So these would be our salmon, and then the flow of the nutrients will come down, and we have our section which grows shellfish. These are the extractive species. We have our area for microalgae, and then we have our novel species also. So to go into a bit more detail about our the species that we have produced on site, our fed species is salmon, and in support of the salmon cultivation, we also include cleaner fish. For those of you who are familiar with salmon production, one of the biggest obstacles that salmon farmers come across is sea lice. It's an ectoparasite, and it causes very many problems, both with regard to fish welfare and economics on a salmon farm. So for that reason, on our pilot site, we introduce cleaner fish. This is lump suckers, which we introduce over the course of the winter to try and maintain those the levels to try and curb the levels of infection of the parasite sea lice. So that they will be our two fed species, the salmon, the primary fed species, and the lumpfish in much lower numbers would also have a fed element. So then we also have oysters on site. We have taken oysters from a local bed within the bay, so we have not introduced an external species of oyster. We are using our local oyster, Oysteria edulis, and there's no threat of introduction of disease into the bay because we have taken the local lobsters from the local oyster bed. You can see here we've had some great growth, and I will go into that in a bit more detail later. We also, one of the species we have trialled were scallops. We did have quite a good success with the scallops. However, sourcing seed to bring into the bay has proved problematic. So for that reason, we have not continued the growth of scallops, and they have not proven to be a species that we will be putting in our defined value chain as an outcome of the ASTRAL project. So then these are our fed species and some of our extractive species. And then, oh, pardon me. So also for the extraction of the dissolved wastes, we have our seaweeds. We currently have two species of seaweed on site. We have Saccharina lutisma and Alaria esculenta, both growing very well, and we see that the introduction of the low trophic grid in the nutrient plume from the salmon, the fish cages, has proven to advance the growth of these. And then we also are looking at growing Echinus esculentus, Paracentrotus livitus, pardon me, our purple urchin. I'm not sure which is the pointer. Sorry, we just... So the purple spiny urchin here, we have introduced those, and these are proving to be one of our fed species also, but they do enhance our circularity on site because we are feeding them with the seaweed produced on site. We have novel species also on site. We have a sea cucumber, which was a benthic feeder, and then we have introduced local lobsters as part of a stock enhancement program. So for the ASTRAL project and the IMTA, we, as I say, we are defining our value chains, and we are evaluating each of the species for the value chains based on the crop performance, looking at the capital expenditure and the operational expenditure. We're looking at our circularity, we're looking at the environmental input. We are carrying out with partners in the ASTRAL project life cycle assessments and circularity assessments. So these are underway, and we are looking at the remediation and the ecosystem services that can be provided by these value chains. The evaluation of cultivation methods is one of the things that we're looking at. We're looking at where the species are more developed, and we're looking at how we can refine the methods to optimize the production and become more efficient to feed into the circularity and to produce sustainable crops. We're looking at the creation of standard operating procedures, which we will then be able to disseminate to the monoculture producers within both our own community and further afield to try and enhance the adoption of IMTA. And then we are looking at how technology can optimise our production and minimise environmental impact. We are looking at optimising seed harvest, the timings of those, how to maximise crops, how to investigate performance and yield, and how to optimise our production methods. So, for instance, in the case of the seaweeds, we're working in conjunction with our colleagues in SAMS. So the previous presentation you have just seen about things like the density of seeding and optimal growth depth for our species of seaweed. So with regard to our native oyster, we're looking at the feasibility of growing these. We're looking at 3 different treatment areas, so close to our, on the low trophic grid, close to our salmon production, and then 2 other locations to see the effect the proximity to our fed species will have. And we're also looking at the different types of containers that they should be produced in. The individual shell height and weight are being assessed, and we have seen that there's been low mortality. There has been successful growth in each of the locations, and we are looking at restructuring our sampling protocol to increase the frequency and the sample selection. So you can see here that they are growing well, which is it's successful for us, as this is the first time that we have grown oysters in integrated multi-trophic aquaculture. And you can see that the growth is increasing and that the optimal growth is currently closest to the low trophic grid. So then with regards to the macroalgae, both the Alaria asculenta and Saccharina latisma have seen to be grown very well on our low trophic grid. This compares very well with previous projects where the low trophic grid was not in place. So we have seen success within the instigation of the use of that area and that grid. The growth rates have improved in the years, and to increase the circularity on site, we are looking at, we feed the urchins the macroalgae that we have produced on site. So the impacts of the seaweed culture, we can see that there is a significant positive effect on the environment by remediating influence of the fish, with early results showing that there is a reduction in nitrogen of 11.5%, phosphate of about 20%, and carbon of about 17%. We've also seen that the harvestable tonnage, the density on the lines is 9 kilograms per metre at the farm gate. So this is all very, very positive. So then we try to define why IMTA and why we should to promote this type of IMTA, so an open water IMTA with the top species, the fed species, down to our extractive species. So IMTA diversifies production systems and creates an indirect and direct benefits. So the benefits include the reduction in ecological impacts. It is a move from a linear model to a more circular model, which enhances the ecosystem approach. It provides waste reduction within the industry through bioremediation. It also improves societal perception of the aquaculture, which we all know is very important. IMTA grown products have an advantage in the marketplace, and we are also doing investigations within the ASTRAL project about how IMTA products can fit into certification standards. The IMTA also optimises space availability so that numerous products can be produced in one space effectively and efficiently. There is commercial benefit to growing species together on the site. This shows itself in the use of labour, the use of equipment. All of the labour and equipment can be common among fish production and the low trophic production in terms of people and boats and things like that. So that's always very, very beneficial. And diversity provides alternative incomes and cash flows, increasing the resilience of the business. So I suppose, to use an analogy, all your eggs are not in one basket. You have your crop spread and your income spread over different species and different times of the year. Another element of the IMTA process is complementary seasonality between your products. So then beyond biomass, the true value is in the ecosystem services and the nutrient trading credits that the low trophic species provide at the farmed gate. And I think that this kind of approach to farming at sea is going to become more important as our policymakers see the benefits in reduction in carbon through our farming practices. So thank you very much. We can take questions at the end. We have one more presentation for you now. This concludes the presentations on the 4 IMTA labs that are actively producing species. The next IMTA lab that you will be presented with is our prospective IMTA lab from Argentina, to be presented by Thomas, and he will talk to you about all the investigations they are doing to see how best IMTA could be introduced to Argentina.
Okay, thanks, Pauline. You already said my first minutes of my talk. Okay, well, I'm Tomás Chalde. I work together with Clara in Argentina. And as Pauline said, we don't have IMTA facilities in Argentina. And that's why our work in the frame of ASTRAL is just to think how to develop IMTA or how to promote the use of this type of systems in Argentina. Here is where we work. This is the Tierra del Fuego Island and the extreme south of South America, the extreme south of Argentina, and the extreme south of the world. We are really close to the Antarctica, and we work in the Beagle Channel that is between Chile and Argentina and connects the Atlantic Ocean and the Pacific Ocean. This is a typical picture of the area of the Beagle Channel with a lot of several mountains with snow in winter and also during summer. The water is very cold, but is quite constant, the temperature around 10 degrees throughout all the years. And as you can see in this picture is the typical land of all the province. So it's a very pristine area with very low anthropogenic factors, very low pollutions. So when we try to develop aquaculture in this area, it is crucial to take into account the acceptability for the society. And in this frame, we think that the IMTA is a good approach to develop aquaculture in this area, in the Beagle Channel. There have been several attempts to produce blue mussel in the Beagle Channel at very low scale, artisanal producers, but they fail after 1, 2, after 3 production cycles, mainly because red tide and presence of toxins in the blue mussels, and all the productions fails. Just to give you some numbers about some context about the aquaculture production in Argentina, here you can see the overall production since the beginning of this activity in the 80s. The productive increase up to a peak of only 4,000 tons. Yeah, this is the maximum production that we achieve in Argentina. And if we compare with Brazil, about 600,000 tons per year, it's barely zero the production in Argentina. And also, if we see here the orange line, this is the marine production. It was even lower than the total global production. So this is an activity that I can say that it's not important in Argentina, but we are trying to be a good activity and a productive activity. And here we can see the species that have been used for marine aquaculture. We can see Pacific oyster, rainbow trout, a finfish, cholga, and blue mussel. And if you see, these both species are exotic. They were introduced to Argentina, Pacific oyster and rainbow trout. And only the blue mussel is the only native species that have been produced for marine aquaculture in Argentina. So we have low production, and also we have used exotic species that we know that is not a good practice to promote. So we have experience of with only one native species to be produced in Argentina. So when we start in Astral, the first question that we asked was, which species have the potential to be produced in Argentina, and specifically in an IMTA? And when I say which species and which is the potential for this species, not only, I don't talk only about the species, but all the factors that we have to consider around this species and how to select the species. For example, we need to know which systems could be used for this species, and in the context of the Beagle Channel, if open system or land-based systems, the regulation that exists, environmental condition, market, social acceptability. Again, this is crucial. This is the bottleneck that we have at this moment, or one of the bottlenecks. So what we did was a long list of all the native species in the Beagle Channel that could have some kind of potential to be used. It doesn't matter if it's high potential or low potential, or at least some interest to be produced in aquaculture. We divide these species in 4 groups, depending on the role that they could achieve in an IMTA system. These are fed aquaculture, typical the finfish, the high trophic levels, the 2 organic extractive aquaculture species for sediment or suspended material, and the inorganic extractive aquaculture species, typically the macroalgae, the low trophic level. And all these species, we analyze gastronomic value, the knowledge that we have about the biology of this species, biology, genetic aspect, physiological aspect, ecology, and so on, and the aquaculture knowledge that we have or other people around the world have about this species. So we have a lot of questions, and the good is that there are much more data than we think. Also in Argentina, with no traditional activity around aquaculture, we have a lot of data about the species that could have been used in this type of system. The problem that we have is this, that we need to move from basic research to interdisciplinary applied research. We have a lot of data, but at a scientific level with experimental research, but not, we never think about how to produce these species. So we gather a lot of data for each species. Here, for example, is Patagonian blenny. It's a finfish located along the south coast of Chile and Argentina. And we gather data about biology, the maximum length of males, females, the weights, the maximum age of the females and the males, the growth curve, reproduction type, the spawning season. And we see that we have data for all these characteristics, and also about the aquaculture condition, at least at experimental level, about survival in captivity, data about growth in captivity, how the reproduction can be managed in captivity. Here is an example in more detail. Fertilization rate, again, for the Patagonian blenny, for this finfish, the fertilization rate can achieve up to 90%. The hatching rate, again, 90%. The larvae survival of this species at 10 days, 30 days, we have data that could be between 70 and 80%. And we have a lot of data for all these species. Then we need to sell these species, not only to grow them. So we need to know about the market. We made some works trying to understand which is the best species in the market, or which is the species that the seafood restaurants are selling. And here we can see the species that the seafood restaurant offer in Tierra del Fuego. And for example, here we have the southern king crab that about 80% of the restaurant always offer this species. And again, we have for all the species, which is the market. The second species in importance is the blue mussel. So this is a good opportunity because we already have some previous experiences about how to cultivate this species and also have a good local market. Here, trout and salmon, two exotic species. Again, they have a good market, but we don't want to use exotic species. Finally, with this data about the market, about the biology, about other data that we have to how rare these species in captivity, we use the DEXI tools. DEXI is a software, a free software that helps us to select species in this case, or any other aspect that you want to analyze. It's a very simple tools. You know how to use it in just one day. And here, what we did was for each group of species, depending on the role that they have in the IMTA systems, we analyze, for example, the reproduction in terms of if the full cycle is achieved in captivity or not, the reproductive manipulation, what we know about the larva feed, the larvae hatching, the fertilization rate, also data about the market. And you can assign values for each one of these categories, for example, for fertilization rate. Again, this is, I don't remember for which species, but here you can assign 0 if the fertilization rate is extremely low, or even if we don't know how is the fertilization rate, if we never did any experiment to determine it. And these programs then shows you all this data in these simple graphs. Here we have Patagonian blenny. This is the silver side. Odontestes smithi is very similar to Odontestes argentinensis that you have here in south coast of Brazil. Here is Pushen, is small fish located in Argentina, Chile, and also in New Zealand, and is commercialized in New Zealand. And here we have a red octopus, and you can see, for example, for silverside, we have a lot of knowledge about reproduction in captivity, and the opposite is red octopus, that we don't have many knowledge about how to manage this. The reproduction of this species. Then the DEXI program, the DEXI software, gives you these tables with weak points and strong points of each species. And here, for example, for Patagonian blenny, if we see that the full cycle, the value is 0, this is the weakness point of this species for aquaculture, then we can think to increase our jobs, increase our experiments, to research how to increase the possibility to fulfill the life cycle in captivity. The same for the other species. And finally, this is what we are proposing for Argentina. These are our best species with the highest potential at this moment. For fed aquaculture, we only have one small fish, the Pushen. Also, we have these two sea urchin, but they can play a role also in fed aquaculture, but also in organic extractive aquaculture. Then the southern king crab is a species that is, the aquaculture of this species is very advanced, but only for restock wild population, not for biomass production. The blue mussel, and two algae, ulva, and halophytes that is present in Tierra del Fuego Island. And that's all. Thanks.
So thank you very much, Thomas, for that presentation. And now it's over to you. It's time for your questions. So what I might ask is that if you have a question, obviously raise your hand and you might introduce yourself and what organisation you're from, and then we'll answer your questions. And then to follow on from that, because this is a workshop, we would like to get your opinions. So, number one, please. So we will take this opportunity to ask you some questions. But first of all, the floor is open to you for questions for myself, Luis, or Thomas. If you have anything that you would like to comment on, or even, we would like to open the discussion to see what your thoughts on IMTA are. No? Okay, well, so we have one or two. Okay. And
hello. Yes. My name's Liesel. I'm with the CSIR in South Africa. And I'm not an aquaculture person, so I'm like a satellite data and harmful algal blooms person. And it's absolutely fascinating to learn so much about aquaculture. In the first instance, I was really struck during Luis's talk that essentially IMTA is trying to replicate the development of ecosystems that took millennia on this planet. So I think it's a very impressive undertaking, and there's this wonderful work being done. But I wanted to ask possibly a silly question, which is so for example, in the Irish IMTA, with the salmon tanks, are all of these species restocked from larvae or from eggs or whatever every production cycle? Or is there any kind of sort of reproduction of each species within the system? Is it always an external addition, is what I wanted to know?
The answer is yes. We stock from juveniles which have been produced in hatcheries. Mainly, there's a full freshwater cycle for the production of salmon from egg to smolt, and then for lumpfish they're produced in hatcheries also. The seaweed, again, is hatchery grown. The only exception in the Irish IMTA lab is where we sourced our oysters. We got them from as small oysters on the local bed. They were fished by the local fishermen, and we took the smaller of their catch to be able then to on-grow them, just to prove that we could actually allow them to grow in our IMTA system. But yes, we are in the situation that every species we do farm has to come from a hatchery setting. And maybe we can ask, Luis. Yeah.
I'm quite interested in this in terms of the additional risk, essentially, because it seems to me, especially in the open water systems, there's just risk everywhere.
Our situation is the same. We introduce new organisms or new young fish or shrimp or algae in the system every time. Sometimes this can be a problem, especially when we introduce animals from other parts, and then we can introduce some disease in the system. This is the big problem, especially when we move animals or juveniles or seeds from other regions to our place. So this occurs with salmon, with trout, when move fingerlings from Norway or Europe to Chile, for example, when we move shrimp or PLs from the northeast of Brazil to our lab, but everyone make this. So.
And to add on to that, in the case of Ireland and the Irish species that we deal with, the aquaculture industry is highly regulated. We have to have licenses and permits and vet checks, veterinarian health checks on any of our species before they are moved from the hatchery locations into the open water. So to try and mitigate against any cross-infections. We also have with regard to oysters, there are particular bays within our country where oysters are not allowed to be transferred out of due to the incidence of an infection called bulimia. So there are restrictions on the movements of certain species. So it is all highly regulated. Okay, we had one more question from this gentleman here.
I would like one question for Luis, technical question. What is the relation in the surface of the shrimp culture, tilapia culture, and seaway?
Okay, for shrimp, I told you about the densities, but we have tanks with 16 tons to 4 and 4. So we have the relation 4 for 1. Okay, 4, 1, 1. Yeah.
Did I see one more hand?
Hello, my name is Gonçalo. I'm a researcher from the Faculty of Sciences of Porto University. So, Luis, you mentioned that at the moment the seaweed biofilter is not as good as you would like to see regarding the nitrogen. So, is there any room for improving, the setup, the cultivation system, increasing productivity, or because you just mentioned that maybe we just need to look into something else? But actually, ULFA is regarded as one of the best biofilters that you have out there. So are your productivity numbers, and even if I remember right, even the nitrogen level in the biomass goes up in this bioflux system. So is there any work that you can do regarding productivity and try to optimize that, or you're just gonna be looking to something else?
Yes, probably yes. We can improve the absorption, especially of nitrate. The phosphate is close to 90%. It is very, very high, the consumption, very, very high. But the nitrate is around between 27 to 35%. So to improve this, the idea is keep this algae or the halophytes more time in the system, especially during when decrease the temperature. This is our next step. We have some problems. We had some problems. We have different results in the same system because the temperature and the total suspended solids. So now we know about the total suspended solids, and the temperature. Maybe this is the biggest stressor for the algae or the plants in general. So the idea is produce shrimp and tilapia during our summer period, then introduce after when you start after the summer period, introduce the algae and the halophytes in the system, and see what happened during the period with reduced temperatures. Maybe they enjoy the place and the ingrowth better. So maybe this improve the nitrogen, especially nitrogen consumption. Maybe this is alternative. Other one is try to find other macroalgae to work. But we start to work with the local species, and uva is one of them. But maybe, if not possible, work only with uva, try to other kinds of plants. We work with salicornia, grow a lot in the system, no problem. And we try now with New Zealand spinach, and another one is how is the in English? I'm trying to. Okay, it's salsão. You know, salsão, I don't know, in celery. Yes, this is one. Celery. So we can find other species to work in the system. The puzzle we start to move the piece, so we can do a lot with this. Yeah.
So have we any more questions? Okay, I might ask, there's another lady just came in at the back there. So let's just run down through the questions, and please feel free to answer in Portuguese if that's easier for you. So let's just begin. We want to get your interaction about your involvement and your perception of IMTA. We're gathering as much information from stakeholders in the Atlantic area where we're holding these workshops to try and gauge the interest in how IMTA can be moved forward, and then how best we can go about engaging current monoculture producers to tempt them into expanding into the IMTA, to use IMTA systems. So let's just go down through the questions, and you can stop me at any stage if you're not certain about what we're trying to ask you. So of course, question number 1 is, are you an IMTA producer? Then if yes, we'd like you to let us know which species you culture. Are you aware of IMTA production systems in your jurisdiction? And if you could possibly give a small description of what those systems are in that space, that would be very helpful. I might just give you a moment or two to answer those questions, and then we can move on. So the next question is with regard to national policy. So are you aware of a national policy in your country? And if so, do you know, is integrated multi-trophic aquaculture part of that national strategic plan? Again, if you'd like to maybe give some detail there, if you do know something about the planning for aquaculture within your jurisdiction, that would be very helpful. Okay, the next question is about potential. So what can you see is the potential for IMTA in your aquaculture area, or for those of you who are aquaculture producers at the moment at your site, so where you currently produce species? And could you please mention the species that interest you and the type of system that you would be able to culture. Okay, I see that some of you have actually completed this, so I won't spend too much longer going through the questions. So the next question I have on the list is, what do you perceive as current obstacles for IMTA development and commercialisation? So what would be the bottlenecks or the roadblocks preventing IMTA from being practiced in your jurisdiction? Okay, the next one is, do you consider integrated multi-trophic aquaculture to be a more sustainable production system? So that's yes or no. And we're nearing the end now, so in your opinion, what is the most sustainable IMTA system? So the choices are open water aquaculture, either freshwater or ocean, land-based flow-through systems or recirculating aquaculture systems, RAS systems, aquaponics or other. So you can make your choice there. And then I suppose a very important element of what the whole ASTRAL project is about is pertaining to research. So what research would you like to see carried out to help realise the potential of IMTA? So what would you see are the necessary components for the research community to carry out to be able to prove that IMTA is the potential future for aquaculture? And then the final question is, what research avenues or objectives can inform and facilitate IMTA regulation and policy developments? So what questions do we need to answer to be able to promote IMTA with our policymakers? And then finally, if you would like to get a report about the outcomes of this workshop, or if you have any questions, please put them in the last box along with your email address. So particularly if you have any questions for the South African lab or for our colleagues in the Scottish IMTA lab, if you want to jot the questions in there and give us your email address, we will attempt to answer those questions for you. I see some people are still busy writing, so I'll give you a few more minutes. But for those of you who are finished, you can either leave the sheet of paper on your seat. And I'd like to thank you all very much for attending today and for your participation. Please do take a look at the ASTRAL website for more information about the project in its entirety. And there are contact details there if you have questions about any of the IMTA labs or any aspects of the project. And as we say, this session this afternoon was recorded, and eventually this video will be made available on the ASTRAL YouTube channel, where you can also find more information about the IMTA labs and other presentations that have been given over the course of the project. So thank you again, and I can bring this workshop to a close now. So I wish you all a very good conference. And then just one last reminder that there are more sessions from the ASTRAL project in this room tomorrow afternoon, along with another workshop which is looking at the technology advancements within the ASTRAL project. Thank you all very much.
Thank you all for your assistance today. To close the day, I will remind that tomorrow we will have the last session of the conference at 1 here in this room. This session is an aquamatch session for aquaculture career networking for early career professionals, where we will have very interesting talks from professionals in aquaculture. After that, we will have the ASTRAL Workshop on community inputs for recommendation for monitoring of the effects of climate change and emerging pollutants in the aquaculture sector. So we expect to have your attendance tomorrow, and by today I will close the session. Thank you very much.